Hello. Hi, Kevin. Have you been here before, Kevin? Also, can you tell me if you can hear my audio? Because I was looking at a playback of my old live stream. I didn't like the audio quality. Can you guys hear me well? Or you guys want me to like change a method? Anyone want to say anything? Hello. Can you hear my quality? Like, is it good quality? Like, can you fully understand what I'm saying? Or do you think it could be better? Okay. As long if it gets to a point where you don't understand what I'm saying, just tell me, because I think I have a microphone on my laptop. I think that the microphone on my earbuds got water damage, and I was like drinking from a water fountain or something. So yeah. Also, it might be a little bit noisy today. I'm trying to insert something to my USB port. There we go. Hey guys. Okay, I'm gonna start in like 1 or 2 minutes to see if everyone gets in here. Get some things pulled up. How you guys been though? Have you guys been to my stream before at all? Or you guys met me before? No? I feel like there's always new people every single stream. I feel like there is also another Kevin. Rachel? Oh, did you go to my first one or my second one? Because the second one was a little bit embarrassing because I didn't know how to do a problem. But I talked to, oh, dang, you were in both? I can tell my first one was a lot better. But if you remember the question from last week, it was about like two cars, right? And they were going at two different velocities. So the one at front was like going faster than the other. And they both brake at the same time, right? And it was this problem. And I couldn't figure out how to solve it because like with the kinematics equations, there are like way too many unknowns to actually solve it. So I talked to like a couple of friends of mine, and like I couldn't quite find like a direct kinematics solution to it, but there was like a trick that they told me to use, which is like because like the faster car, well, it's like this weird like conceptual thing where you like if they as long as like their x happens to be the same thing at a certain point, as long as that x doesn't become the same thing, then that means they don't collide. It's kind of weird, but I'll be honest with you, I still don't fully understand the question. The fact that like the second car is going faster implies that like it won't collide into the first one unless like the acceleration is slower, but it's a little weird. Okay, anyway, so just really quick for those of you who haven't met me, I kind of like went through my introduction in my last two streams, but I'm gonna just introduce myself again because, you know, why not? Hi, I'm Casey Lee. I am originally from Henderson, Nevada, or more specifically Las Vegas, Nevada, because a lot more people know Las Vegas. And I'm currently attending university to become a mechanical engineer, potentially an electrical engineer. We're going to see what happens. But yeah, I'm in my dorm right now at Columbia University. So like it might potentially at a certain point become loud because I think there's a residential event happening in my dorm hall eventually. So yeah, bear with me for that. But for this week, I have some exciting problems prepared for you guys. But if you guys have any questions concerning physics in general, you can drop it into the chat. We can go over those first, specifically if they're kinematics related, because the theme right now is kinematics, and kinematics is fun. So did you guys have like a test recently, want to review for a test coming up, have like a homework question that you want help with? Just drop something into the chat and I'll see it and then we can go over it. And I just do like very general physics content because once again, I'm taking the same physics classes right now, but for mechanical engineers. So it's a little bit more advanced, not very, but yeah, I'm just gonna get started. If none of you guys have any questions for now, But yeah, let me pull up my Canvas. Share screen. Okay, last week Crowdcast was being a little bit dumb. Now it's showing up my paint canvas. You guys see that? Yes. You guys seen graphs before? I hope you guys have. Okay. So no questions at all this week? If not, I'm gonna go with the initial plan for the week, which was to like cover these graphs. I just realized something. Oh, you're typing a question? Okay. While you're typing a question, I have another thing I must talk about. So I've been, Amanda, who is like the CEO of this company, has told me that I should pick like 2 like good viewers or something, like superstar viewers. And out of all of the streams today, 2 people will eventually get goodie bags. So if you guys are like actively participating or like being very good viewers, like asking very relevant questions, you could be selected, but that is completely up to you. But yeah, regardless, Kevin, I'm gonna let you type up your question. Is it gonna just like make sure to leave it inside the chat, because like the way my screen is set up, I'm going to be like looking at the chat primarily. But for now, I'm gonna start with this velocity. Oh, here it is. Pretty lame question, but can you give a general explanation? Velocity. Well, that's perfect because we have a velocity graph. Okay, let me give you a brief, like, for those of you who want to conceptually understand. That's perfect, because do you see like these graphs? I feel like these graphs are probably the most relevant way of understanding velocity, displacement, and acceleration, okay? So just really quick again, I keep on asking this question every single week because it's one of the most relevant things when considering physics is, do you understand calculus? And if the answer is no, that's not bad. Okay, if you understand calculus and understand integrals, drop a yes or a no in the chat. Especially you, Kevin. No? Pre-calc? Okay, that's fine, because somewhat, that's very good. AB Calc, even better, because like I think that there is nothing that goes beyond AB Calc. Like there's no BC comp that you need to understand. But in general, with Physics 1, you can like understand very, very, very general ideas about calculus and still be able to get along. Okay? So I feel like we always start with distance, velocity, and acceleration, right? You can tell that there's a relationship between these 3 values. But the current question is, what is the relationship between these 3 values? And like the calculus way of saying that is that distance, okay, we can say that distance is itself, right? But velocity is, okay, let's use the correct units. So distance is in terms of x, whereas velocity is in terms of dx dt. And if you don't understand dx dt because you haven't taken calculus, you can consider it as delta x, delta t. So the change in distance over the change in time. And if you think about the units of velocity, which is in meters per second, that makes sense. So for every, the unit itself implies that it demonstrates a change in distance over a change in time. Now, if you want to look at acceleration, ooh, where's my thing? Oh, it's over here. If you want to do acceleration, it's the second derivative of distance. And when you take the second derivative, that implies it's the first derivative. Oh, wrote that wrong. First derivative of velocity. And now you might be wondering, like, what exactly is a derivative? When I say it's a derivative, I mean that it's the slope of a graph, right? And we're going to very quickly go over that when we do these graph problems. And I think that it's easier to understand the other way around, right? So how do I get from acceleration to velocity and velocity to distance? And we're going to cover that in the very first question over here. Number one, what is the displacement, right? And we currently have a velocity graph, right? And you might be thinking like, ooh, how am I going to relate velocity and time? So the opposite of a derivative is an integral, right? And also stop me if I don't make any sense at all, because I feel like sometimes I like get ahead of myself and I don't want to lose you guys. So if you guys have anything you need to clarify, just drop in the chat and I'll see. But I said earlier that that velocity was a derivative of displacement, right? Then what is the opposite? So how do I get from velocity back to displacement? And that is something called an integral, right? An integral is the area under the curve. And this is extremely easy to demonstrate. Okay, so let's take this velocity graph right here. Let's say I want to calculate the displacement until 3 seconds, right? So we know that this velocity times time is equal to displacement, right? This is on your like kinematics sheet, but it's really, really obvious, right? So if you go at 5 miles per hour for 1 hour, you travel 5 miles, right? Pretty simple, really intuitive, and probably some things that you've covered since middle school, right? Like basic algebra. But then how do you calculate if the velocity is changing? What you do is find the area under the curve, right? And that makes a lot of sense because one dimension is velocity and the other dimension is time. And you know, velocity times time is equal to distance. So that is kind of a not super calculus way, like kind of like the bridging between the gap between calculus and pre-calc, right? You can find the area under the curve of this graph to find displacement. So if you were to look at this one, 3 seconds, 3 meters. I wrote this wrong. This is supposed to be meters over seconds. We can just do simple 1/2 base times height is equal to displacement, right? And in this case, the base is time and the height is velocity. And it's pretty much the exact same concept. So this displacement from 0 to 3 seconds, I don't know what I'm writing, is going to be 4.5 meters. Everyone see how I got that? Because 3 times 3 is 9, divided by 2 is 4.5. And that is just calculating the area of this triangle. Does everyone understand that? Just to make sure I'm not losing anyone. Okay, that's good. So let's try to calculate the displacement over this area. Let me use a different color. Let's use red over this area. This area is even easier, right? So there's constant velocity. That means it's at the same speed the entire time. Whereas the beginning, it's becoming faster, and that is also known as constant acceleration. And I'll go over like how to get the acceleration graph of this. But right now we're getting displacement. So can like someone in the chat tell me how you would calculate displacement from 3 seconds to 12 seconds? That's not necessarily true. Anam? Am I saying that name right? Final minus initial? Final minus initial what? So velocity? Okay, the final velocity is 3 meters per second, and initial velocity is 3 meters per second. So 3 minus 3 is 0. But the thing is, there's no 0 displacement. Oh, time. 12 minus 3 is 9. So you go for 9 seconds. But how do you find the displacement? So you just once again, just think about this graph. Distance is equal to velocity times time. Yes, find the area by finding the base. Okay, yeah. So final minus initial. 12 minus 3 is 9 seconds. And the height is going to be 3. So yes, 9 times 3. So I should probably be keeping track of this. Okay, let's officially keep track of all the numbers with you. So this 4.5 meters. Here is going to be 27 meters. Over here, we can kind of cheat a little bit because we know that this is symmetrical. So pretty much it has the exact same dimensions as earlier. This is like 3 meters. Not 3 meters, 3 seconds. This is 3 seconds. The height is 3 seconds, and 1/2 base times height is 4.5. And you can clearly tell that this is probably not drawn to scale because I drew it. But, okay, the final one is a little bit tricky and definitely requires a little bit of calculus. But I was like, might as well throw it to you guys because I know a lot of you guys understand how to take a really basic integral. How big? In terms of if it is negative on the positive. I just realized how big. Hold on. I mean, in terms of velocity, if it is negative. No, that's not necessarily true. And I'll get over. Okay. So do you see that this area is slowing down, right? The velocity is negative, and it's currently in the positive. Yeah, it's currently distance is still positive, but the velocity is negative, but does not necessarily mean that there is negative displacement. It's just that the rate of change in us going a distance, so dx dt, is negative. When it's just decreasing. It's not necessarily negative. So what you're probably thinking of is acceleration. So if it was below zero, like velocity is below zero, no, it doesn't. Yeah, displacement would be negative because let me draw. Let me draw another thing. Okay. So imagine you go here, right? Let's say that the graph goes under, and you find the area under here, right? So let's say that this is like 1 meter per second, but what am I writing? 1 meter per second. This is -1 because it's below the x-axis. So the y dimension would be negative. And once you find the area of that, it would be a negative area, right? So you would subtract that from the total displacement. So technically, yes, you are indeed going backwards if you're going at a negative velocity. Does that answer your question? A little bit? Okay, sounds good. Okay, let me try to do all this. Okay, let's take an integral. Okay, this is a more mathematical way to approach it. Okay, and you can do the exact same thing if you like graph out all of these lines. You can do the exact same thing I'm doing right now. So what I'm trying to do, I didn't even put the timestamp on this. So let's say this is 15 seconds and say this is 17 seconds, right? Ooh, I don't know where that went. 17 seconds. Okay, so let's take the integral. Integral means area under the curve of x squared dx, right? That means you need to take n plus 1. Let me just think about this for a moment. Yeah, so you take n plus 1. If you understand how to take an integral, you'll know what's happening. But basically, the integral is 1/3 x cubed, right? Because you do n plus 1 over n plus 1, right? I feel like you calculus people can understand that. And that's 1/3 x cubed, and you just take the displacement. Wait a second, I'm being stupid. Dx dt. I'm being a fool again. Regardless, you're supposed to be inputting 2 in here. And it should be 2 times 2 is 4 times 2 is 8, so 8/3. So the area beneath this would be 8/3. And you can just like take it like a typical like x squared graph and find the area beneath it. And you just integrate the limits with the time. Because, yeah, I think it's because I set up the axes the other way. But yeah, it's pretty simple. So my second question is, what is the average velocity? Right? And let's just kind of ignore this last x squared part of the graph because I don't like the numbers. I don't want to compute 8/3 into my average because like 4.5 plus 4.5 is really simple. But yeah, how do you guys think we should compute the average velocity. It's like just conceptually thinking about what it means to have an average velocity. How do you guys think we should compute this? Anyone have any input? Yes, very good. Okay. So once again, you can think about the units of velocity, right? Where's my, here it is. I keep on losing my mouse. Velocity is equal to meters over seconds. That's units, right? So basically what Megan is saying is that we should take all of the meters, all the total displacement we have just underwent, and divide it by seconds. So I should actually calculate the full displacement before I continue. But I don't want to compute 8/3. I didn't think hard about this when I actually calculated it. I actually made this up. But I mean, you get the point of how to find the area under the x-squared graph. But for now, let's just do 4.5 plus 4.5 plus 27 is equal to 36. So let's say the total displacement up until t equals 15 is 36 meters. The average velocity, you can take 36 meters divided by 15 seconds. So that is the total distance divided by the total time. And yes, exactly. This is just basically what Megan said. I can't make it more complex. But yeah, if you guys have any questions, once again, just make sure you stop me. Okay, so what am I moving like? So in my head, I was gonna do a demonstration of what is happening here, down here with my lovely little astral circle, right? I don't know how I'm gonna do this yet. Ooh, stop that. Okay, so I guess the beginning, you have an increasing velocity. So you start at 0, you start at rest, right? And come on. So you increase velocity at a constant rate. My circle's not agreeing with you. So you increase velocity and maintain that velocity, and you slow down, right? So I feel like this is really simple. And I guess the way you can see that is you're in a car, right? And you're starting at rest or at some sort of constant velocity. You don't really know. No. I don't know what I'm talking about. So you're sitting in your car and you're at a certain x. We don't really know what x it is, but we just know your velocity, and you're increasing in velocity. That implies that you're adding some sort of force to increase your speed, right? Or your velocity. And that is why velocity is increasing. So you're basically pressing on the gas pedal, right? And from time 3 seconds to time 12 seconds, you pretty much let go of the gas. And for some reason, your brakes, I don't know, the friction between your wheels and the axle of the wheel is really small. So once you let go of the gas, you don't slow down. You just maintain that constant velocity, but you don't add any more energy to the system to cause you to speed up, right? And now when you slow down from 12 seconds to 15 seconds, you're basically applying the brakes, right? You're applying the brakes until you come to a full stop, or delta x. The change in x becomes 0, basically. Well, not the total change in x, but you're not moving a distance x anymore, right? So you're pressing the gas, coasting, and then pressing the brakes, slowing down. And that is called deceleration. And then at the very end, that basically means that you're speeding up at a very extreme rate, at a non-constant rate. So you're basically pressing the gas pedal, right? Let's assume that when you press the gas pedal, you maintain a constant acceleration. It basically means you're pressing the gas pedal even harder. So you're speeding up even faster, right? So that is basically what is happening in that final part, okay? Part 4, draw the displacement graph. Okay, this is the part, I guess. You guys might like, let's see. Oh, I don't like that. Let me do a gray. Did you guys know that Fiveable has very, very, very specific colors? So I'm technically supposed to use Fiveable gray whenever I'm doing everything, but I secretly don't a little bit. Okay, so we have a graph. Okay, I'm just gonna draw this with, oh, I just got rid of my color. I'm just gonna draw this with like my brush because I feel like, do you see this like x-squared value? It was really hard to draw with like the lines and stuff, so I'm just gonna draw this by hand completely. So this would be time, and this would be displacement, right? So at the beginning of the graph, the velocity increases, right? So, okay, let me try to explain this in a way that's like not very calculus-like. Okay, so perhaps you'll understand this flat section of the graph, right? So let's start at 3 seconds. Okay, and this is like 4.5, and then we go a distance of 27, so the next one would be 31.5. And then 36, yeah, 36 up here. And this is all in meters, which is really nice. Okay, so let's just do the middle part first so that you can kind of see what is happening here. All right. So let me start 3 seconds. We already made it through 4.5 meters. Then we keep like a constant velocity. So we're slowly like going and driving at 8 miles per hour, and every single hour we basically increase like, no, hold on. We're going at 3 meters per second, and every second we increase in 3 meters. And that sounds very familiar, right? That's basically just 3x equals y. That is like the analogous equation, right? 3x equals y. And I guess you can say like plus 4.5, right? Can you guys see the like similarity between there? If I say that I'm driving and every second I pass, I increase in 3 meters in distance, you guys can see why it's like 3x plus 4.5, right? So I guess the graph over here is just, I don't know. The graph over here is y equals 3. 2 miles away, if the person's would the displacement be a shorter distance or a longer distance? Okay, displacement. Displacement implies that we're on a coordinate system, right? Okay, I'm gonna like go to the bottom and just like kind of demonstrate. And I feel like the best way to demonstrate these, like a problem where you're on a cliff and you're throwing a rock, right? These are pretty common inside a lot of kinematics problems, right? We either talk about x displacement or y displacement, right? So it doesn't matter if like this ball like goes this path, like let's theoretically say some sort of in some sort of like weird magnetic field, but it ends up here, right? It ends up here where it started, right? That means that x displacement is this distance, the y displacement is this distance. I don't really care what path it took, because the displacement in the end is pretty much the same. Velocity is always dependent on a direction. Like it's vector based, right? like you can have velocity is equal to, I shouldn't get into vectors. I don't want to get into vectors because that might like be a little bit more confusing, but just understand that vectors have an x component and y component. And let's say you're like going at like a 45-degree angle. This will be very helpful when you have like forces, when we start talking about forces, right? You need to like separate the components to like the x and the y. So like the normal force, you're going to need to break that up into the x and y components. So basically, yeah, you can take a different way of getting somewhere, but like we need to set it up in a coordinate system for us to be able to manipulate it. Okay, so I'm gonna get back to where I was. So I'm gonna try to cater to people who know calculus and don't know calculus at the same time, right? So over here we have a graph of like y equals 3, or velocity, or the y graph is equal to 3. And once you take the integral of it is 3x plus c, right? And if you know how to take integrals, it's a pretty simple calculation. And the plus c ends up being a 4.5 because of the displacement over here, right? So that's pretty simple. That's just a straight line from here to here. Yes. But these graphs over here, right? These aren't straight lines. This is the graph for this guy is just x, right? No. Y is equal to x, and y is equal to negative x plus some constant. Negative x plus. I don't want to think too hard about it because all I'm really taking is like the area beneath the curve and adding it on top. But you understand what's happening here, right? Y is equal to x. So how am I going to draw a displacement graph for that? That kind of means that like you're speeding up. So you're in a little car and you're like going faster, right? It's not a straight line, but you're going faster, and it kind of imitates some sort of x squared graph, right? And then at the end, you have this exact same type of acceleration. It's basically the exact same thing you had here, but translated over here, right? So can you guys see where I got the displacement graph? Oh, no. This one is slowing down, so it's backwards. So yeah, this one is slowing down, so it's gonna like kind of taper off a little bit. So it's gonna like it's going fast, but it's going like slow. It's becoming more flat, basically, and that's pretty much the entire graph. And if you want to do the last part, it's gonna be an x cubed value. And like honestly, I don't know how to draw it at this point. Like it's gonna be like flat and like extreme acceleration. That is the displacement graph. And you might notice that at no point is it like the slope is negative. There's no point where it's slowing down, right? And that's because like no, it is slowing down at this point. I lied to you guys. What I'm basically saying is that the displacement never dips beneath, what am I trying to say? The slope doesn't go under because we don't ever go in the opposite direction. That is what I'm trying to say. Okay, are there any questions, or am I going too fast, or am I going too slow? Do you guys want me to cover more things? Because we can go to the acceleration graph next. I feel like the acceleration graph is a little more exciting if the velocity did go below the x-axis. Okay, so let's take the original example of how we had. Let me choose a different. So let's say it goes down here, right? Let's say that it continues to dip, right? And do you guys remember velocity goes negative x. Let's take this part, delete it, and then it'll basically, all that will happen is that this will go down, right? So this corresponds, if you remember like the x squared graph, because the slope is negative, it looks like this, right? Basically, when it crosses the x-axis, it's gonna be this like top maximum point, and it's just gonna go down. And if it keeps on going down, and maybe eventually it'll go negative. That's when like the area beneath this graph and the area beneath this graph balance out, and the displacement starts becoming negative, and the graph for the displacement graph will dip beneath the x-axis. Does that make sense? Yeah. I know it's a lot of graphs, and if you guys get really good at graphing, I highly recommend it. Graphs are so important. I thought I could run away from it at some point in high school, but let me tell you, if you understand graphs, you can unlock a lot of new ideas. Okay, show the acceleration graph. I think the acceleration graph is super easy, right? Sometimes the way I think about derivatives and integrals, at least when I was in high school and I was just learning these things, that like the integral typically makes graphs more complex, whereas a derivative makes graphs more simple, right? So let's say you take the derivative of like an x squared graph, right? And it's like this weird loop, and it's like super complex, right? Once you take the derivative of that, it just becomes a straight line, right? That's why converting from velocity to acceleration is like so nice and easy. And like once you get the hang of it, it's pretty, it just becomes second nature. So let's draw another. Ooh, I don't like the color either. Let's just use some Fiveable colors because I love to stay on brand. Okay, let's see. There we go. Okay, and then let's do acceleration. Oh, that's cheeky. Oh, I didn't want to do everything. Acceleration, and then time. Right, and technically these go on forever. Whatever. Okay. So for this first part, let me conceptually make you understand what it means to be a derivative, right? I explained this a little bit last week, so I'm just gonna say it again for those of you who didn't hear me last week. Let's use this nice burgundy color again. The derivative is basically the slope. So you look at this, right? And the slope here is pretty much 1. The slope here is the same. The slope here is the same. The slope here is the same, right? Slope here as well is pretty much 0. And you're going to see what happens when we have that. So let's say the slope here is 1. The slope here is 0. And the slope here is -1, right? And the slope here, I know it's really messy. Sorry about that. I was thinking about getting like another like photo editing software up. I do have another one that has layers, so I can just delete a layer some other time, but that'll probably be next stream, not this stream. But this final one, if you take the derivative of x squared, is going to be 2x, right? And like if you don't understand calculus and why that is, you just take the derivative of x squared to get 2x, and if you don't understand that, that's completely fine. You don't need to know that to ace the physics one exam. Okay. Oh, shucks. Computer's running out of battery. That's okay. So let's do this first part, right? The first part, the acceleration is 1, because we know that the slope is 1. Okay, so let's do the same time. 3 seconds, 12 seconds. Let's do the acceleration because it's easy for x squared value. And once again, you're going to see how much this simplifies, right? That is the first 3 seconds. I know the lines aren't like touching, but I'm trying my best here. Can you guys see why I just drew a straight line? And I should probably write down this. This is 1 meters per second squared. Do you guys understand why I just drew a straight line? Anyone not understand? Like it's because like the slope for that entire portion is just 1. And it's pretty nice and easy that way. You can see how it simplifies a lot. And you see, how can you simplify a straight line? It just simply becomes 0. You're not becoming faster, you're maintaining the same velocity. So this entire section is just flat, right? And then you do another portion where it's just -1. Pretend it's straight. It's supposed to be straight. I know it's not straight. This is -1 meters per second squared. Step this part down. So when we get this 2x squared value, we know that the derivative is 2x. So I don't know how long this is going to take. Let's just say this is 16 seconds here. And this is 2 meters per second squared here. And then we're just going to have a big old line that has a slope of 2. Oh, yeah. Okay, that's basically the entire graph. You guys have any questions before I go on to the second part? Anything that makes sense? Anything that didn't make sense? Like any sort of like feedback? Oh, also I see that there's 2 ask questions. Kevin, you asked that one earlier, so I got you ready. Yes. Okay, any questions right now before I continue? Oh, okay. That's cool, Kevin. I'll wait for you, but let's take a preview of the next question. This one. Wait. Did I do everything I needed to do for this one? Okay, we could change this into a displacement graph, but for the sake of time, I think it's better for us just to continue because I think that this graph is really exciting. I mean, it already looks pretty exciting, right? Is that cool? Hold on, let me grab my charger. Make sure things are charging. Okay, that is a very good question. And that question makes 100% sense, right? And it's not always 90 degrees. Like if you look at this last one, this isn't 90 degrees, right? But simply because this drops from 1, okay, you can tell that this isn't like a normal break, right? I keep on like highlighting this, probably makes no sense. But do you see the yellow here? This corner right here, you can definitely tell that there is a distinct change in value, right? This goes from the slope of 1 immediately to the slope of 0. And for the sake of physics 1, where like most of these graphs where like velocity is pretty much constant and you're not going to deal with like very high accelerations where like the acceleration is going to change. For the most part, in in algebra-based physics, it is going to be like looking like these types of graphs where it's just like these really right angle things happening here, right? The only time that it really doesn't look like that is when, let me try to think. I mean, I already gave you the example of this guy right here. Like on the end, this went from 90 degrees to like straight. But as long as you keep on thinking about the slope, like at a most fundamental level, if the slope has like a really stark change, then you're going to see that stark change in like another graph of like some sort of derivative. Does that make a little bit of sense, or do I need to like explain it in a different way? Yeah, okay, that's good. And also just like once again, taking the derivative of these graphs and taking the integral of these graphs, the steps pretty much are the same, right? Once you take the integral, you can see that, like, do you guys remember when I drew the displacement graph? I already lost it, but if you look at a replay of this live stream, you're going to be able to see it. But like, if you can look at the displacement graph, if you go from the displacement graph, you can go to the velocity graph. And like, my sixth question over here is like, what if we change all the units and made this into a displacement graph? Then this velocity graph would be the acceleration graph, basically. Wait. If I change this to displacement, I'm just like getting confused over my orders, but where's my pencil? It's over here. Okay, so displacement, velocity, acceleration. We're currently at acceleration. So if I had a displacement graph, if this were to become a displacement graph, then the acceleration graph would become, basically everything gets shipped down like up one. But I'm just putting a lot of words in my head and like trying to explain it. It's probably not making a lot of sense, and I completely understand that. But what I'm trying to say is that if you isolate these graphs just to pure mathematics and you completely ignore like what is happening inside the macro scale world and like interpret these graphs as like x, like two different variables, two different sliders, then you can see like how like these graphs can be like derived very easily. Okay. I should probably stop explaining more before I confuse you guys more. Okay, but once again, we got 13 more minutes before I have to end the stream. So if you guys have like any questions beyond graphs, this is your last chance to ask them. Okay, but meanwhile, I'm gonna talk about this graph. So have you guys seen this graph before? Like at least in math, right? You guys have seen this graph. Can you guys name what this graph is? Cosine? Yes, you are completely correct. This is indeed just a simple cosine function, right? Okay. So my question right now is like, what is going on here? Right? So you're starting at a high velocity. You're starting at one velocity and you're slowing down and you're going backwards. Okay. Let's break this graph down, right? I mean, zoomed in too far. So we're going really, really fast at the beginning, right? But we're slowing down, but we're going the same direction. But at a certain point, we stop, we turn around, and we speed up in the opposite direction. And then we stop, and we go in the positive direction and speed up, and then slow down, and then we stop, and then we turn negative. Can you see why that's happening, right? That's just like me trying to verbalize what is happening inside the velocity graph. I'm gonna hope that I'm making sense. Okay. Do you guys know what the derivative of velocity is? I guess like what I would prefer is like the integral of velocity. Do you guys know what the integral of velocity is? Not velocity, of this cosine function? Yes, that's what I'm trying to say. What is the integral of cosine? Anyone? Okay, this is like probably Fact 1 stuff that you'll cover later. But in fact, you know what, let's just try the mundane method where we like actually think about the slopes, right? So let's actually draw this out. Where? So the slope here, right? The slope here is 1. The slope here is 0, right? You take this, find a tangent line, then 0, right? So you start here. Slope here, you take the tangent line, right? Slope here is negative. Actually, the slope here is at its maximum. So the slope here is at its maximum negative value, right? It's going to be about -1, right? You can kind of see that it's going at a -1 style. If you kind of look, the rise and the run kind of looks like -1, right? We'll go back. So you go here, and there's the slope of this graph. It's 0 again. So here, it's a very positive one. So we go here. Can you guys kind of guess what is happening? Here, the slope is 0. You guys see the graph that's happening here? No? Yes? Negative slope, -1. Go down here. Slope is 0. We go up here. And you connect the dots. Ooh, what does that look like? That looks like a negative sine function. So the derivative of cosine is negative sine. Pretty cool, right? And that kind of implies that no matter how many derivatives or integrals you take, like you can have like the derivative to like the 50th power, and it would have the exact same shape, like the wave shape, but like shifted over, or you can say like it's reflected over. A lot of different ways to say it. But like basically the cosine wave is just a sine wave like shifted over or the other way around. So I just took the derivative of velocity. Do you guys remember what the derivative of velocity was? The graph I drew here was acceleration. Right? And you can see that. I'm slowing down, right? And then here, I'm speeding up, it's positive, and then here I'm slowing down. So that is the acceleration graph. Okay, I feel like the displacement graph is a little bit more difficult to understand. But let's think about it in terms of like the area under the graph, right? So here, okay, so you got this area under the graph, right? You start at like 0. You start with 0 area under the graph because the distance in time is 0, right? So you start at 0 over here. And then you have this area, and this is like it's at its maximum, right? This is a max amount of area, implying that there's already area over here. So this is its maximum, right? And over here, I think I'm like purposely confusing myself. Basically, this is its maximum here. So it goes up, and then some of this area starts negating this area, right? So like this area subtracts from the red area. So this starts to go down. And basically, once it hits here, it's basically negated everything that was here, right? So the displacement is 0. And if you keep on thinking about this, oh, I should have used a different color. It's just gonna be like a mirror image. Let me redraw this in like purple, right? I'm not sure if it's just gonna make it look more ugly, but yeah. The purple is a displacement graph. Math is kind of beautiful in that way. I love sine and cosine. It's just all from like the relationship between like right triangles. It's kind of absurd that you see this like really beautiful relationship in calculus. But after drawing all of these like graphs, can you guys guess like what sort of situation in real life this would happen? Can you guys like throw me out some like guesses on like what's happening here? Like, is this like me walking down the street? What's happening? Anyone, any guesses? Anyone out there? I wonder out there. Can you give us a guess? Is this like, okay, this is actually a really common like physics problem to have. So this is just like a hint out there. Actually, like I was really inspired by this like class that I'm taking right now in physics. But this is a very, very important physics phenomenon. Walking backwards and then forwards forever. Very good. That's very, very close. Yeah, back and forth. Okay, what goes back and forth? What goes back and forth? Like, think about like all the things you do in physics class, right? Like all the physics experiments. What do you do? Like, what is a common experimental setup where something is going back and forth? I feel like my hand motion might help. Like back and forth like this. Like, pendulum. Yes. What else? Anything else? How about a spring? Like a spring, once you like displace it, it like goes back and forth, right? And in fact, like you might see that this graph is like a wave, right? In fact, this simulates waves in general. It's like kind of this like freaky like meta thing. Like the graph looks like a wave, and in fact, like it looks like a wave in person. It's this strange relationship between like math and reality. I think it's really interesting. But basically, this graph represents simple harmonic motion. So this is like an entire unit inside AP Physics 1 that can be simulated by this simple graph. Right? Isn't that pretty cool? Right? Let's see. Let's see what questions I have. I already drew the velocity. I drew the acceleration. Okay. Some quick questions before I leave about this graph in particular. So let's say that I end at, let me draw like a big old color scheme. I should really think of colors before I start. Okay. Let's say, oh, there's too many colors. Even I don't know what's happening. I don't even know which one is which anymore. Okay. This big old black line ends right here, right? So the velocity is like this. So what would be the average velocity between t equals 0 and t equals, let's call this final, t final? What would be the average velocity? Any guesses? I know that, what was your name? Megan earlier had an equation for displacement, like average velocity. So what would be the average velocity of this graph right now? Like from t0 to t final? Any guesses? Well, anyway, I'm just going to go over it because we're running low on time. So let's say that this is 1 and this is -1. 1 plus -1 is 0. So the average velocity balances out, right? So what's going to be the displacement? Displacement is also going to be 0 because this area cancels out this area, right? So even though it's constantly moving side to side, and let's say that it perpetually doesn't like have any sort of dampening, so it's not slowing down, the average velocity is going to be 0 depending on the time you're at. Like after like as t goes into infinity, and you're gonna see this at like Calc 2, Calc BC, which is currently irrelevant to you guys, but like just for funds, like once t goes to infinity, the average velocity will approach 0 overall. Yeah. If a graph like this were to go on forever. Displacement? Okay, just think about pendulum, right? It depends on what your t is. Oh, my ugly drawing over there. Okay. So you got pendulum, right? And like let's say the maximum height is here, and the maximum height is here, and it's oscillating like this, back and forth forever, right? So let's say that like a t equals alpha, the displacement in terms of x will be whatever this distance is. However, at t equals beta, it's going to be here. So in simple harmonic motion, it really depends at what time you're talking about displacement and what time you're talking about velocity, right? And just like a really quick fun fact about simple harmonic motion, at these ends, velocity is equal to 0. It stops, in fact, right? And you can see that happening here, right? Velocity is equal to 0. Velocity is equal to 0. Velocity is equal to 0. Velocity is equal to 0, right? And let's assume that the x direction is positive. Positive x is this direction. Negative x is this direction. This is decreasing in velocity. So this, and this time, the pendulum is going this way. At this time, assuming that this is a pendulum, it could potentially not be a pendulum, right? And this, the velocity is negative. Wait. Oh, the velocity is positive here. I made a mistake. So velocity is going this way. So it's swaying this way. Here it's swaying that way. Here it's swaying this way. For on and on and on for all of eternity until it gets dampened or like kinetic energy, like total energy is lost and it just stops. Well, like technically it doesn't ever fully stop in an ideal system, but yeah, that's pretty cool, right? Yeah. Anyway, that's the end of my stream for this week. If you guys want to like see more of our practice sessions, let me actually put this video up to full screen. So I do these live streams every single Thursday where you can like bring your problems and just like pretty much ask me anything you want. If you guys don't have anything, which I feel like this week you guys didn't have as many questions as usual. Like I always have practice problems prepared for you guys. So next time, if you have a test next week, you can tell me right now. I can prepare me too. If you have homework next week and you're stumped, I purposely made this stream Thursday night because I feel like tests and homework is usually due Friday night. Yeah? I mean, I was a high school student 2 years ago as well. So like I feel like homework and tests are due Friday. So yeah, just come to me and we can like, just hang out, talk about physics. If you guys want to just talk about physics, I'm also down. I really enjoy physics if you can't tell. But yeah. Thank you guys for coming. I really appreciate you guys showing up. Hope you guys come back next week and we can talk more about physics. Okay. I'm gonna sign out now. Okay, thanks for coming, you guys. It makes me happy to like think that I'm helping someone out there. Okay, bye.